Hey folks, there are lots of different types of problems and different types of problem-solving techniques. In fact, generally there are two types of techniques for problem-solving. One is the intuitive approach, and the second is the more analytical approach. With the intuitive approach, you're essentially trying to take a shortcut, not think things through precisely, but use forms of prejudice or expectations that are generally true, that you expect will work out, but you can't be sure, but you're going to take that chance. And, in a way, we do this when we're walking down a street and we see someone and we make an evaluation of whether they're going to be a potential threat to us or not, based on a very limited amount of information. And this is good because we need to do that quickly. We don't have time to think it through. So that's type 1. And you can also, with type 1, say, well, I saw it work this way this time. This seems pretty similar, so probably whatever I'm looking at will work the same way, without carefully analyzing whether, in fact, that is an appropriate connection between the two. Now, the analytical approach takes longer, and you have to work at it more, and that's where you would go through a rigorous analysis, step by step, looking at the interrelationships of variables, how they relate to each other. This would be something that, if it was a quantitative approach, that you could actually calculate. Now, for the intuitive, it doesn't take as much brain space, and by that I mean consciousness. It really is quite amazing how limited our consciousnesses are. I'm sorry, it's true. We store vast amounts of information beneath consciousness, which can be called up like in a hard drive, as an analogy, but there's a very limited amount of working memory, either in the RAM or the flash drive now. So there's a technique, if you're doing kind of an analytical approach, is to come up with shortcuts that you know are going to work based on past experience, and also by creating subroutines. And what I mean by that is modules which you become so good at. Maybe an aspect of algebra would be one of these modules. Language, the whole structure of relationships would be one of these modules where you could say, if this increases, then this will decrease and this will increase, and you can kind of work that out and do it without a lot of thought, because essentially what happens is the more these subroutines become second nature, the more space you have in your consciousness to hold the problem in mind. So essentially what happens is that you can create more space by having things become second nature. Now, a lot of that, in our, cerebellum, those are things that in that location of the brain, it stores muscular movement. And that's basically all just stored where you don't have to think about it. So you can just say, I want to move my hand, I want to ride a bicycle, and it all gets worked out. But you can do the same sorts of things when you're thinking about problem solving. Now, a couple things that interest me about how we can go about breaking problems down and making them simpler. One of the most brilliant things in working out what happens when particles interact, disintegrate, and change is something called a Feynman diagram. A Feynman diagram essentially is a way of dealing with the fact that there are literally an infinite number of things, but we can write them down discretely in these little cute little diagrams. And what this allows us to do, Feynman diagrams are quantitative, that is, you can take them and you can score them numerically. The only problem is that you have to create an infinite number of them to get a completely accurate answer, but you can do enough of them so you get pretty close. And since Richard Feynman's death, they have been able to mathematically rework this to get cancellation of a lot of these interesting diagrams, and as a result they've gotten much, much better results. But it's essentially his work that did it. But what I'm sort of getting at is the problem was intractable because of our limited consciousness. In other words, it was hard for any person to get a handle on it. It was overwhelming, and he created a system where we could break it down. And essentially what happens is that the probability of a particular interaction of particles is based on everything that is possible. That's why it becomes infinite, with certain possibilities becoming far, far less probable. And you have to kind of work this out. But if you look at it that way, it looks like a mess. But if you look at it as, okay, let's draw this diagram, let's draw this, and you draw them, you can work on them discretely. And what that does is it allows your consciousness to take some of the information and push it away, not deal with it, so you can deal with those little pieces. So that's, well, it's kind of logical. But a lot of people don't think about it, because when I tutor people, they don't take advantage of this. For instance, if you're working on a physics problem, if you take the information and you put it down really nice, you can forget about some of it, so your consciousness can focus on something else, and then it will be right there. But if it isn't right there, if it's sort of written in text all over the place that you can't find it, your consciousness is too small to deal with that. You lose it. You can't see the whole problem. So by doing that, it's a really good graphic technique. And making a diagram and creating vectors and all that kind of stuff when you solve this problem are all ways of dealing with the fact that we are so limited in our ability to see problems. Now, certainly some people have greater abilities than others, but all of these techniques are very useful. And that's why when you see, for instance, an organic chemist working on some complex series of reactions or some kind of organic problem, they'll always be writing as they talk. It's just like second nature. But students won't do that because they don't understand that trick. Now, another case, which by the way is also a quantum phenomena, occurs in organic chemistry. And what happens is electrons behave like waves. They also behave like particles. But there's something called delocalization, where electrons can exist over 3 or more atoms. And when this occurs, it's very hard to deal with. Because if you have a large molecule and the electrons are all over the place, human beings have a hard time visualizing that, seeing that, understanding that, because their brains are so small. So what they have done, and it's kind of like the Feynman diagrams, is they've created a series of diagrams, but they're not quantitative, they're qualitative. And they look at individual cases with specific rules, and they say that all of these cases represent a part of the truth. But if we draw the whole truth,